I'm Ricky Pimentel, and I'm a PhD student in biomedical engineering at UNC and NC State. My goal is to help people age gracefully so they can stay active and healthy throughout their lifetime. Compared to young adults, older adults require more energy to walk at the same speeds, which impacts their endurance and independence. A major theory on this higher metabolic cost is the shift in muscle work from muscles spanning the ankle to those at the hip. When shifting muscle work, older adults tend to rely more on muscles with longer fibers and shorter tendons. This requires older adults to perform more active muscle contraction and less passive tendon stretch and recoil, which may lead to higher metabolic costs by literally taking the spring out of their step. When young adults push off the ground with less force while walking, they redistribute muscle work just like older adults. So, we wanted to test this shift in muscle demand theory in young adults because it can control for other age-related changes that affect walking economy. It's not really feasible to measure the metabolic cost of individual muscles during walking. So we used musculoskeletal models to calculate the muscle forces required to generate movement, and then estimate the metabolic cost of each muscle individually, accounting for muscle fiber length, activation level, and tendon elasticity. We asked young adults to walk at their typical speed when targeting their normal push-off or propulsive force, as well as 20 and 40% lower than normal, shown in blue. We also asked them to target 20 and 40% higher than normal propulsive force, shown in orange, but we don't discuss that data here. We recorded their motions and forces during each of these trials and also measured how much oxygen they consumed to calculate their actual metabolic cost. Our model estimates of walking economy explain about 1/3 of the variance in directly measured metabolic cost. The metabolic cost of walking increased when targeting smaller propulsive forces, just like in older adults, mainly explained by muscles spanning the hip and the knee. The increased cost of muscles spanning the hip when targeting smaller propulsive forces mostly occurred around early stance. With less ankle push-off, the leading limb's hamstring muscles had to work harder to maintain forward progress with each step. During leg swing, targeting 40% smaller propulsive forces led to higher metabolic costs to operate muscles spanning the knee. The quadriceps had to overcome insufficient ankle push-off by performing more work to swing your leg forward and straighten it before the next foot strike. Our work highlights the importance of ankle push-off during walking and how muscle compensation at other joints can lead to higher metabolic costs, even in young adults. We need to find ways to maintain ankle power capacity using rehab therapies and assistive devices. Ultimately, this would improve walking economy in older adults so they can keep moving forward with active and healthy lives.